Hello everyone. So we're on to another example, and in this example we're asked what is the pH of a solution that results from adding 25 milliliter of a 0.12 molar hydrochloric acid solution to 25 milliliter of a 0.4 molar solution of ammonium. All right, and this is an interesting question. So we first need to think a bit about the situation. So first, let's just discuss the hydrochloric acid solution. So hydrochloric acid is of course a strong acid. So that means the species that is present in the hydrochloric acid solution, just so that we understand our symbols that we'll use. So if you put hydrochloric acid in water, it of course is a strong product forming reaction in which hydronium is formed, right? Hydronium, and then there's some chlorine ions present. So for strong acids, the acid that actually does the reaction or actually does the reacting is hydronium, right? Because all of the acid ionizes to hydronium, and that is always why we say the concentration of HCl, right, because it's a strong acid, is actually equal to the concentration of hydronium, because it all ionizes to the hydronium ion. All right, so when we're adding HCl to ammonia, the question is, what is the reaction that is taking place? Well, that means once we've added the two solutions, the reaction that takes place must be hydronium plus ammonia, right? Ammonia aqueous. So let's even draw our little beakers. So this is our volume of HCl, which is 25.0 milliliter, 0.0, and it has a concentration of HCl, which is 0.12 molar, and we add that to a different beaker, right, which has a volume of NH3 equal to 0.43 also 25 milliliter. It has a concentration of ammonia of 0.43 molar. Alright, so that's what we're mixing. And because we're adding a strong acid to, even though it's a weak base, we still expect it to be a product forming reaction. So what forms during this? Well, it's an acid-base reaction. The acid should protonate the base, so it should form NH4 plus in aqueous solution, and then that's left over is the deprotonated acid, which is just water, right? So that is what is formed, and that is in one of the beakers. So let's give that a different color. And what we need to remember is that this will have a new volume, which will be of course V total. We can already see that's going to be 50 milliliter. All right, cool. So now the question becomes one of stoichiometry, right? Because we can see we have a certain amount of acid, right? Certain amount of HCl, which is equal to the hydronium ion concentration, which can react. We have a certain amount of ammonia, which can react. And then there's ammonium that forms in a certain, and all of these things are in a final volume, which is 50 milliliter. All right, so that gives us then, and only then can we start discussing on what is the thing that's actually dictating the pH, right? Because that is what we're interested in. Because we're interested in what is the pH of this final solution here. And to determine the pH of a solution, we need to know, is there only one species present? Is there two species present? Is there, because that dictates then the pH. If there's only a strong acid present at in a solution, then the pH is quite simple to calculate, because for a strong acid, the pH is equal to whatever its concentration is, because that's equal to the hydronium ion concentration. For a weak base, we need to do an ICE table. For a weak acid, we also need to do an ICE table. If it's a buffer solution, we can use Henderson-Hasselbalch. So we need to determine what kind of solution we are left with here. So let's turn back to what we were adding together. So what was our amount of HCl? In other words, what was the amount of hydronium that we added to the solution? So that's equal to the volume HCl multiplied by the concentration of HCl. And if I do that, take those two numbers there at the top, multiply them together, of course, volume in liter, I get 3 times 10 to the negative 3 mole HCl, which is of course equal to 3.0 times 10 to the negative 3 mole hydronium, right, which is able to react with our ammonia. Our ammonia is of course equal to the volume of ammonia multiplied by the concentration of ammonia, and I get here 0.01075 mole NH3. And maybe it's also useful to write it in scientific notation, so that is 1.075 times 10 to the negative 2 mole NH3. Okay. So what we can see from these two, if we start comparing now what our two reactant number of moles are, which I hope you see. So we see we have a 1-to, firstly we have a 1-to-1 reaction, right? The amount of hydronium, or the amount of HCl that reacts with ammonia, is we have a 1-to-1 reaction. So 1 mole of hydronium reacts with 1 mole of ammonia. And we can see that from our numbers there, that our ammonia is more. So right, if we even write it a bit more, the same base number of significant or scientific notation, then we see we have 10.75 times 10 to the negative 3 mole NH3. Alright, so that means we have essentially, so we have 10.75 versus mole ammonia versus 3 mole hydronium. So if it is a 1-to-1 reaction, that means the ammonia is in excess and the hydrochloric acid is our limiting reagent. Alright, you can do the limiting reagent calculation in full if you want to test that. Highly advised, because you have to write it out, but I mean you should be able to kind of see that now. This is a very simple one. So therefore HCl is the limiting reactant Right, and NH3 is in excess. The question is by how much is NH3 in excess? So let's put here NH3 excess, or the amount of NH3 left, is of course how much we had initially, NH3 initial, minus, well, I'm going to write it here as the amount of HCl, right? Because it's a one-to-one reaction. So, meaning that how much ever HCl reacted will be the amount of NH3 consumed. And then I get a value here of 7.75 times 10 to the negative 3 mole NH3 left. Let's say left after reaction. Alright, so that just shows that there is an excess of ammonia. So that answers our first question. So all of the acid is consumed, not all of the base is consumed, not all of the ammonia is consumed. So there's some ammonia left. Now the second question is, what of the product? So there's of course ammonium that forms. So how much ammonium forms? So of course the amount of ammonium that forms is dictated by the limiting reagent, right? It's always dictated, so your amount of reactant or your product that forms is dictated by the limiting reactant. So the amount of NH4 plus formed is equal to the amount of HCl multiplied by the stoichiometric ratio. So there's 1 mole of NH4 plus for every 1 mole of HCl. In other words, for every 1 mole of H3O plus that reacts. Okay. And of course you can write it as 1 mole of NH4 plus per mole reaction, 1 mole of H3O plus per mole reaction, to be, if you really want to. So you see it's a 1-to-1, so that means we have 3.0 times 10 to the negative 3 mole NH4 plus that formed. Alright, so what does this solution contain? It contains ammonia, 7.75 times 10 to the negative 3 mole of ammonia, which is left after the reaction. And we also formed ammonium during the reaction. So what do we call a solution when there is the base as well as the conjugate acid? Because what is NH3 and NH4's relationship? They differ by 1 proton. We have the base and its conjugate acid, both in significant amounts. We of course call that a buffer solution. So therefore this is a buffer solution that forms. Because why? Because NH3 and NH4 plus are present. Alright, and how do you calculate the pH of a buffer? Well, you use Henderson-Hasselbalch. Okay, so pH is equal to pKa plus log of the concentration of the base divided by the acid, the conjugate base divided by the acid concentration. Now, if you recall, you can directly use the number of mole of each of these species, but we can quickly calculate their concentrations. So let's substitute in everything. This means we must take log minus log of the Ka value, plus we are interested in log of the base is NH3, the acid is NH4 plus, of course, right? So just here off to the side, the concentration of NH3 is equal to the 7.75 times 10 to the negative 3 mole divided by, what is our total solution volume? It was 50 milliliter, right? After we mixed everything together. So that's 50.0 times 10 to the negative 3. So you can calculate that. And our concentration of NH4 plus is equal to 3.0 times 10 to the negative 3 divided by 50.0 times 10 to the negative 3 liter. So of course also in liter that. And hopefully you can remind yourself that you can see that's why the volumes cancel, so that's why you can actually just directly use the number of mole. And our Ka is equal to, so the Ka that we must use is the Ka of ammonium, of NH4 plus. So if you look that up, it's 5.6 times 10 to the negative 10. All right, plus log of 7.75 times 10 to the negative 3 divided by 3.0 times 10 to the negative 3. So notice that I'm going to just use the number of moles. You're welcome to use the concentrations to check whether or not you get to the same answer. So use those concentrations, calculate the concentrations and see if you get to the same answer. And if you then round to 2 decimal places, because it's pH, so 2 significant figures, I get 9.66. All right. And this was a very nice example of where you didn't expect to get a PA or a buffer solution, but by reacting, having a limiting reactant, the acid being a limiting reactant, and having the conjugate acid forming during the reaction, you actually formed a buffer solution, implicitly formed a buffer solution. All right. So it shows you, it's not always just you have a buffer solution that's like you make up a buffer solution or whatever. Sometimes the buffer solution can be formed implicitly by something that happens. So always remember what a buffer solution is defined by, and be on the lookout for that. All right, thank you for watching, and I'll see you in the next video.